Okay, well, it is about 12:30 Eastern Time, so we'll go ahead and get started. We are recording this webinar. My name is John Mann, and I'm an assistant professor at Michigan State University, and I am the host of the series Innovations in Agriculture and Rural Development, which is sponsored by the North Central Regional Center for Rural Development. So I want to welcome everybody to our webinar today. The title is Removing Emerging Contaminants in Drinking Water by a Novel Carbon-Based Enzymatic Reactor. So before we get started, I want to highlight just a couple of things real quick. First of all, like I said, we are recording this presentation, including the questions and answers. So if you would like access to this, I've put a couple of URLs in the chat box below. One is for the NCRCRD site, and the other is for the Innovations in Agriculture and Rural Development YouTube page, and so you can get access to the recording there. I also have mine and Dr. Lynn's email in the chat box below for those who wish to reach out directly. And finally, the presentation itself will be about 25 minutes, and we'll have about 15 to 20 minutes for questions and answers. So as your questions come up, please enter them in the chat box below, and we'll get to those at the conclusion of the presentation. So our presenter today is Dr. Chung-Ho Lin, and he is an associate professor at the University of Missouri. Today he's going to share a little bit more about his efforts to provide clean water sources. So Chung-Ho, go ahead, the floor is yours.
Hi, John. Thank you for your introduction. I truly appreciate all of you spending time with me and give me a chance to briefly present what we have achieved over past 3 years. So my name is Chung-Ho Lin. I'm with MU Center for Agroforestry at the University of Missouri at Columbia. So today I would like to briefly talk about one of our translational research, which is to utilize the carbon renewable resource to construct the enzymatic reactor for removing the organic pollutants in our drinking waters. Okay. So briefly, I would like to talk about the issue of the water quality as a result of industry and agricultural operation. A lot of the drinking water source has been contaminated. Here's one example. Basically, this is a map show you the contamination of the drinking water source by one of the commonly used herbicide, atrazine in the Midwest. Every year, more than 76 million pounds of atrazine were applied in the Midwest, the Corn Belt. Therefore, during from April to August, we can detect the atrazine in groundwater, surface water, in the rain, tap water, drinking water, almost everywhere. Okay, that concentration often is beyond that regulation standards. Therefore, our lab has been thinking whether there's a cost-effective approach can remove these organic pollutants at a large scale level. So this basically give you some background about this concentration of this atrazine in our drinking water. Okay, as I mentioned earlier, between April to August, you can easily find the high concentration of this atrazine in the water. Why we are concerned about this class of the pollutants? Because atrazine has been known as an endocrine disruptor. Now, has a long exposure of this chemical might lead to some chronic disease. So Therefore, this is one class of compound we are particularly interested because the scale of this contamination. Also, we have one study initiated about 2 years ago. We also found the other class of chemicals, including the personal care product and pharmaceutical in our drinking water source. So far, we have identified more than 85 different chemicals which behave like endocrine disruptors. Those chemicals include antibiotic, antidepressant drugs like estrogen, okay, and the beta blocker used for disease treatment, like heart disease treatment. Also, we detect several anti-inflammatory commonly used. Also, we found the antifungal, also recreational drug, anti-seizure, and also some of the drug has been used for lowering the cholesterol. So imagine now we are feeding our people with the water contaminated with these new emerging organic pollutants. A lot of these compounds behave like an endocrine disruptor, or they have a strong biological activity at a very low concentration. For example, a lot of recreational drugs and also the estrogen, commonly found in the birth control pill, with very low concentration of this chemical, it can trigger the strong biological activities. That's why we're very concerned. Okay, now I'm going to lead to one of the technology that we developed. Our team has developed a technology that we can easily, quickly, and to immobilize any kind of enzyme on the hard surface. Those material, the platform material, include, it can be carbon fiber, polypropylene, polystyrene, nylon, glass fiber, carbon nanotube, and magnetic particles. Today, I will only focus on the common base. So many of you probably probably might not know what the enzyme for. Enzyme basically just is like a bioactive molecule. They can catalyze the chemical react or biological reaction, but the enzyme itself will not be involved or will not be consumed by the reaction. That means the enzyme more like a biological catalyst. They catalyze the chemical reaction, and we can reuse the catalyst over again. Traditionally, in order to develop an enzymatic reactor, it involves a very expensive and labor-intensive purification process. Also, conventionally, in order to immobilize this biomolecule in the hard surface, usually also involve a lot of expensive chemical reagent, chemical conjugation. But in our approach, we rely on the E. coli to help us to program and engineer the enzyme that allow us to easily immobilize in the functionalized platform. So there are several advantages of our system. First, our system can be programmable because we developed a genetic cassette so that allow the E. coli to mass produce that engineered enzyme. Also, our system can be reusable because we have a solid platform, and we can easily reuse this system. Also, the system eliminates the expensive purification process, the enzyme purification process. Also eliminate the expensive chemical conjugation process. And another advantage of this system is we can easily regenerate the platform by very rapid and low cost process. The systems so far can be regenerated at least 20 times. Also, we can our technology allows us to immobilize multiple class of enzyme on the same servers. Because sometimes in order to completely remove a certain class of pollutant, usually you will require more than one or two enzymes. Our system allow us to immobilize multiple classes of enzymes on the same platform. They can carry on the reaction and completely degrade the pollutant into the non-toxic degradation products. Also, by having the platform, it also helps to enhance the stability of the enzyme by protecting the catalytic pocket of the enzyme. Yeah, this is one example. This is one of our prototype developed. We first successfully immobilized the enzyme on the carbon fibers. As you can see, let me show you. As you can see, there's the carbon fiber. Carbon fibers is is made of a renewable component. Also, it provides very large surface areas, so that can allow us to immobilize plenty of enzyme on the fibers. So far, we call that bioactive fiber. So we can use this fiber directly for the restoration of the surface water reservoir, such as a lake or stream, or we can pack this fiber into this continuous flow system. So then by feeding the contaminated water through this reactor, you will almost completely degrade the toxic pollutant in the drinking water. In order to help to visualize the activity, we immobilized one of the class of enzyme called beta-glucosidase. As you can see, if we can, here there's the water, okay, with contaminate. So once the water pass through the filter system, is converted, and as a result, you will develop the yellow color. So this is basically just for demonstration purpose for some of our visitor and investor. Okay, and we successfully isolate that gene that encoded with enzyme that can break down the pollutant atrazine. We use our genetic cassette, use E. coli to mass produce that engineered enzyme. Then we immobilize the carbon fiber. So this is one the result from that experiment. So as you can see, the red color represent the percentage of atrazine in the groundwater, which is almost equivalent to 1,000 ppb. Once it passes through this reactor, within 2.5 hours, more than 70% of atrazine was degraded into the degradation products. Within 5 hours, more than 95% of the atrazine was degraded. Within 21 hours, more than 99% of atrazine was degraded. This is particularly useful for restoration of the drinking water source, such as a contaminated lake water or the well water, drinking water source in the well in the rural area. Okay. And one thing I would like to mention, okay, the half-life, that means the persistence of the atrazine usually is about 3 to 6 months, depends on the geographic region and also the climate condition. Usually, the atrazine can stay in the water up to 3 to 6 months. By having this system, we can quickly degrade the atrazine, more than 95% of atrazine within 5 hours. And the blue color represents the percentage of the degradation products. Okay. Feel free to stop me if you have any question. Okay. Right now, we strongly believe we can utilize these systems for large-scale restoration of the drinking water source, including the lake water and the stream water and the contaminated well in the Midwest. So we are thinking about packing this bioactive carbon with the enzyme immobilized on the surface. We pack it into this reactor. We can drop into the contaminated source. This is another advantage of utilize the carbon-based reactor for this remediation purpose. Carbon itself on the surface, they have a strong electrostatic force. So by dropping the system into the water, the carbon itself will attract the pollutant toward the surface, then force the pollutant to react with the enzyme on the surface. So therefore, for this system, you don't need any electricity to drive the reaction. Basically, carbon itself will passively attract the pollutants into the systems. Also, we coated ion with carbon, and we use the same technique to immobilize this carbon ion system. So basically, the system we can easily reuse, and by the simple using the magnetic block, we can easily reuse the systems. At the same time, we try to use the 3D printing technology to construct construct the cartridge. The cartridge serves like a platform, provide a high surface area, so we can use a 3D printer to print the platform with any size and shape, depends on your application. So far, we have developed 15 different prototypes, and one of the prototypes give us the highest surface area that allow us to immobilize plenty of the enzyme on the surface for drinking water treatment purpose. Okay, this give you one example. We have been using some polypropylene or carbon-based material to construct this biofilter system simply using the 3D printing algorithm, and simply after we immobilize our enzyme on the platform, we can simply drop into the continuous flow system, and just imagine they can be used for every household for treating the contaminated water. So another purpose of this project is to add value to these renewable components, the carbon. We're hoping that will help to create some economic opportunity for the rural area. So far, the current the marginal profit for the carbon materials are very limited. Now you're talking about no more than $500 per pound of the carbon material, such as like bioactive carbon or and biochar. The price and the profit has been very limited. If we can utilize this renewable component and add a value to it, and to create this kind of bioactive carbon material, we are talking about increasing the value by at least thousandfold. So far we've been attracting two major investors to sponsor this our current research and development effort. Hopefully in the very near future, we're hoping we can take this technology into the market. So this technology so far has been developed for remediation, water treatment, and also the biofuel production. And we're hoping we can take this idea into another level for biomedical, for agriculture, and for energy application. Yeah, this is the one of the spin-off from this technology. This so far we have this spin-off station in the MU incubator. Here is the some of the angel investor who are interested in our technology. We are also taking this technology to develop an enzymatic system to convert the blood type A, blood type B to the universal blood type O, simply using the same enzymatic process to cut off the sugar on the red blood cell and convert everything into the universal blood. As I mentioned earlier, hopefully one day our technology can be used for food production, for biofuel production, also help to provide another option for water treatment and environmental remediation, and also to improve the manufacturing process for the pharmaceutical or specialty chemical industry. So this concludes my presentation. And do you have any question?
Thanks for that presentation. Let me switch the screens real quick so we can see the questions a little bit easier. So as your questions come up, go ahead and type them into the chat box. It looks like we've got one right now from Amir, and it says, the question is will this be available for larger commercial or municipal scale operations, or at home portable, kind of like a Culligan water system? What about homeowners or schools with well systems?
Yes, that's one of the target market we're interested. We did develop the SBR proposal last year, and the ultimate goal is to develop like a water filter system for the household and also for the school. So that's one of our target market.
Okay, thanks for that. Next question is from Eric. Does this have any effect, impact, or interaction on cleaning water with agricultural runoff, like phosphorus or?
effect also, okay, does that have any effect on clinical? Yeah, these enzymes, they are highly specific, okay, for pollutants. So it will not uh, uh, affect by the phosphorus or nitrogen, as far as I know. So I do believe, just the bioactive fibers alone, it could be used for large scale of the remediation effort, because there are some like a sorbent or some other technology has been developed in the market. They are not designed for this kind of large scale remediation effort. So I do believe that this can be used for cleaning up these some of the chemical pollutants in the runoff, and I don't believe it will affect or it will be affect or impact any like a phosphorus or nitrogen.
Okay, thanks for that. The next question is from Mike. He asks, could something like this be applied to aquaculture? I'm thinking about water treatment for caged fish production. So maybe whatever the waste by the fish.
Yeah, that's another great application, because for in aquaculture, sometimes they apply the atrazine or herbicide in the water to remove the algae. Okay, therefore they will definitely have a lot of herbicide residue in the drinking water and even in the fish. So this can be the great application to remove this herbicide residue in the aquaculture application. Yeah, this brilliant idea. I haven't thought about that, but I really appreciate for these inputs. Yes.
I'm going to inject one of my own questions real quick, and then we'll pick up on Amir's next question. So could you talk just a little bit more about the value added, and specifically what sort of end products are you thinking about?
Okay, that depends on which industry we are targeting. Okay, if we're targeting the agriculture and food and biofuel, we have to rely on the quantity, because the profit margin per unit is limited. Because then in that case we need to rely on the scale. But if we target for the pharmaceutical and specialty chemical industry, usually they'll be willing to pay more, right? So the profit of a margin is much higher. In that case, if we can find a unique use, we could definitely increase the value of this bioactive carbon fiber by at least 1,000 to 10,000 times more. The one thing I haven't mentioned, because we have interaction with several industry in the cosmetic and specialty chemical market. Almost all these market right now, they are start to shift to the enzymatic process in their manufacturing process. One thing is they realize enzymatic process will help them get a better yield. Also, it eliminate a lot of toxic chemical in the process. So one small bioreactor, enzymatic reactor, if you design the process well, it's enough to give like a global supply. So that's why almost all the major pharmaceutical company, they start to shift to utilize an enzymatic process, because it's green. It's also considered like a green technology, also help them to get a better yield. So it depends on where is the market. For pharmaceutical market, we can easily increase the value for every for every unit. But if we target for the food, beverage, and energy or water treatment market, we have to rely on the scale.
Okay, thanks for that. The next question is, I guess, a follow-up from Amir. Do you think, or what do you, who do you think is your preferred market, industry or municipalities? I think this is related to the first question a little bit.
At this point, if we talk about scale, I think we're talking both because we are very early. We're kind of early, but right now we would like to if we talk industry, basically probably we're going to just license that technology. They can scale up from municipality. Now we're hoping now we might be able to design our own like a water filter. Then they can be distributed, widely. I mean, in the U.S. or other country, like in China. China also use I think they apply like a probably 300 million pounds of atrazine every year. The contamination of atrazine also has been one of the major concern for the community. So.
Okay, thank you for that. The next question is from Quinn. What about contamination from oil and gas? Thinking about fracking.
Yes, yeah, that's another market we're targeting. Yeah, I didn't include that in our slide because I'm also involved in the bioremediation of fracking. I've been working with the NGO, government agencies, and university try to develop technology, try to remove a lot of fracking chemicals. So far, we have isolated one of the bacteria, and then we have identified a gene sequence that encode that enzyme. They can break down a lot of pollutants in the fracking operation, like some of the pollutants we're very concerned, such as like benzene and the toluene, and so we identify those enzymes. They can break down the toluene and xylene and benzene, and because like I said, our system can be programmable. So currently we are cloning that gene into our system, and then we're hoping we can develop a system for remediate the contamination of fracking chemicals. Yeah, but we need to identify what are the major pollutants that we are concerned in the fracking operation.
Okay, thank you for that. Okay, next question is from Andy. So the data you showed is for the Midwest. Is that the worst area in the U.S.? What about California or Florida? Are there other countries where this could help? Do you have data on that?
But today I just give the atrazine as one example. Okay, and for atrazine, probably the worst situation is in the Midwest. But there are a lot of other class of pollutants, such as the personal care product, pharmaceutical, is all over the country. I know the California, the drinking water has been contaminated with a lot of personal care product and pharmaceutical. So once we prioritize the list, we can our next step is to develop a multi-enzyme system. So just by passing through the contaminated drinking water through the system, we can quickly degrade several classes of contaminant in one single process. Also, California, the horticulture is another one of major industry in California. So they use other class of fungicides, pesticides, herbicides. basically what I'm presenting is like a proof of concept. As once we identify the problem, we can easily customize our system to address the local contamination issues.
Okay, thank you for that. I see a couple of other folks typing. So one more question from Amir. Do you have a specific target industry? I know you touched on this a little bit with agriculture, but we'll just follow up with this question.
Yes, right now we've been trying to contact several agrichemical company, and also some companies specialize in manufacturing the cosmetic products ingredient, and also we would like to to get this technology introduced into the pharmaceutical. That's the ultimate goal, because the pharmaceutical, they require a lot of FDA approval and process. They have very restricted regulation, but at the same time, the return, I mean, the financial return can be significant. So we are also interested in working with a pharmaceutical company. Hopefully, we can introduce our this system into their manufacturing process.
Oh, thank you for that. So it doesn't look like we've got any other questions. So I've got just one more quick question for you. Would you just briefly discuss your next steps in terms of development? Maybe identify your immediate needs. I know you talked about having a couple of investors, and I know you and I have talked about pursuing SBIR, but maybe just for the audience, follow up on kind of next steps and your immediate needs.
Yeah, right now we have filed the patent to capture the intellectual property. So right now our company is still very small. We have a two investor, and also the probably four scientists working on this project. So next step, we would like to want to capture the investment. It can be through the angel investor, local angel, or venture capital, or also, of course, the government sponsor SBIR program.
Okay, well, thank you for that. Well, it doesn't look like we've got any other questions. So, in wrapping up, Chung-Ho, any parting thoughts?
Yeah, thanks for giving me such a wonderful opportunity to share some our finding with this audience. I really appreciate it.
You bet. Thank you so much. Again, you in the audience, if you would like access to this recording, please visit our YouTube page or the NCRCRD page where the webinars are available. We'll also have the slides put up on the NCRCRD page. And again, my email and Dr. Lin's email is up there in the chat box. Hopefully, I'll get this posted in the next day or so. If you want access. So in closing, I want to say thank you again to our presenter, Dr. Chung-Ho Lin from University of Missouri, and thank you in the audience for participating. And with that, we will wrap up the webinar.
It's my pleasure, and wish you all have a wonderful afternoon.